Okay, this video is for AP Calculus BC section on limits, and we're going to talk about the definition of a limit and finding limits graphically and numerically today. So first of all, the idea of a limit is just this. A limit exists if, as you get closer to a specific x value, but not quite at that x value. So let's say that you're getting closer to a particular x value, like let's say 1, either from the left or from the right, but you stop just short of the 1. You don't actually get to the 1. So you get close to the 1 on either side, right? If you look at what's happening in the y, as we approach from the left here, the y is a number just above 2 here. It's getting a little higher until it's around maybe 2.2, something like that. And as we approach 1 from the right, in other words, from higher numbers on the x number line, right, the y is also approaching a number. And if those two y values, the y value that's being approached from the left and the y value that's being approached from the right, are the same number, then we can say that this limit exists. So the formal definition is this: the limit as x approaches c of f of x is equal to some number n. And what that means is for all x that are approximately equal to c, but not exactly equal to c, so all the x's in the neighborhood of c, as we get close and close to the c, in this case, the c is 1. As we get closer and closer to 1 in x, the y gets closer and closer to a specific number. And as long as it's always getting close to the same number, regardless of what direction we're approaching, then we say the limit as x approaches c of f of x is equal to that number. And this is the notation for a limit. So this right here has to do with the y, right? This part down here, over here, has to do with what x is approaching. So as x is approaching some number, the y, the expression that generates the y, is equal to, and then this is also a y value. It's the y number that's being approached, and that should be a number typically. But technically, the limit only exists if this is a finite number. Okay, so there's a couple ways that you can evaluate a limit, and we'll eventually settle on the one that we're going to use the most. But for now, we'll start with this, that we can just literally plug some numbers in near that target c value. So let's take this particular example here. Limit as x approaches 5 of this expression that produces the y, x squared over minus 25 over x minus 5, right? And it seems like there'd be a problem here, right? If I was actually getting close to plugging a 5 in here, I'm getting very close to dividing by 0, right? 5 minus 5 would be 0, and we know that a fraction divided by 0 is undefined, right? But as we get close to 0, so I can't literally plug 5 in here because that would cause this expression to be undefined. But if I plug a number close to 5 in here, I don't have 0 on the bottom. I might have a small number, but it's not 0. So let's try some numbers that are near this target value of 5. So if we have this number on the x-axis 5, and we want to approach from the left, that symbol for that would be that x is approaching 5. And actually we have a symbol for that. We put a little minus sign right up here above the 5. That means we're approaching 5 from the more negative side of the number line. And so we could plug numbers in here like 4, let's say. We could plug 4 in here. And then we could get closer. We could plug 4.5 in there. And we could plug 4.9 in there. Make this a little smaller here. And we could plug numbers like 4.9 in there, right? And 4.99 in there, and 4.99. So as we're getting closer and closer to 5, right, what's happening as we plug that in? So if you plug 4 and 4.5 and 4.9 and 4.99 and 4.999 into this function, you get these numbers out. So these are all y values: 9, 9.5, 9.9, 9.99, 9.99. This appears to be approaching the number 10. Right? It's getting closer and closer to 10. So we declare that this limit is equal to that number 10. Now, there's a quick way to be able to quickly evaluate all this, and that would be if you have a calculator, you can take the function that produces y and enter it as if you're graphing. So you can say like parentheses, variable squared minus 25 divided by parentheses x minus 5. And then what you can do is you can go to your second window to set the table setting up to be asked for the independent variable. And then instead of graphing, you can say second graph to get to the table and then plug numbers in here. So you can plug in 4, 4.5, 4.99, whichever numbers you pick. This will allow you to quickly plug in by just specifying what the numbers are that you'd like to plug in. And then I can see what's going on here. I can see these numbers 9, 9.5, 9.9, 9.99, and so on. So as 4 is getting closer and closer to 5, as x is getting closer and closer to 5 from the left, the y is approaching 10. All right, so use calculators if calculators are allowed. This would be very tedious to do by hand. All right, and then we also want to approach from the other side, because for a limit to exist, we have to be able to approach from either side, and the y has to approach the same value. So if we're approaching 5 from higher values, that's written this way. X is approaching 5 with a little plus sign, meaning we're coming from the more positive side. That means we're maybe starting at 6 and then going down to 5.5 and then 5.1 and then 5.01 and 5.001. And if you plug those numbers in and you get these numbers, 11, 10.5, 10.1, 10.01, these numbers are also approaching a 10. All right, so we would say the limit as x approaches 5 from the left is equal to 10. The limit as x approaches 5 is approaching 5 from the right is also equal to 10. And since both of those right and left sided limits, sometimes this is called the left hand limit and the right hand limit, if they're both approaching the same number, then we can declare the limit without specifying a direction here is just equal to 10. All right, so that's the idea of a limit. And then the first one in your practice packet is set up so you can try this on your own. Let's say we want to evaluate the limit as x approaches 4 of this structure. You have to check from the left and you have to check from the right. And there's some suggested values to plug in. So you can pause the video, try these in your calculator, write the numbers in that you get, and then what are we approaching as the number here in the middle. Okay, so if you were to try this, you would get, let me write some numbers in here. You would get, if you plug 3.9 in, you get 0.34483, 0.34483. If you plug 3.99 in, you get 33445, 0.33445. If you plug 3.999 in, you get 0.33344. Then from the upper side, if you start at 4.1 and plug that in, you get 0.22258. If you plug 4.01 in, you get 0.33223. 4.001 is 0.33322. And then you look, so these numbers seem to be approaching a value. Now you can't actually plug 4 in because you'll get something divided by 0. Actually, you get 0 divided by 0, and something divided by 0 is undefined. So technically, right at 4, that's undefined. But the limit, right, this seems to be getting closer and closer to the number 0.333, just repeating. Same thing on this side. So that suggests that the limit is 0.333 repeating, which is just the fraction 1/3. So the left-handed limit is approaching 1/3. The right-handed limit is approaching 1/3, and therefore we can declare the limit is equal to 1/3, or in decimal 0.333. Since you can always approximate a number with decimals as long as it's accurate to 3 numbers after the decimal point. All right, so this method is just called direct evaluation, or using a table where you're literally plugging numbers in. Now sometimes you're presenting with information in a graph, so they'll give you a graph of the function. Right? If you have the function that's related to limit as x approaches 5 of x squared minus 25 over x minus 5, if you graph this function, right, it actually looks like a graph of a line. Of course, you can't actually plug 5 in, so there's a hole in that graph right here at x is 5. So you can't actually plug the target value of 5 in. But if you evaluate from the left, right, if you use the table, you would see that this is approaching 10. This is the same one we did on the first screen there, and approaching 10 from the right. So if you just are given a graph, then you can just visually see that as I approach, x approaches 5 from the left, you can just look at what's happening in these y's. These y's are getting closer and closer to the number 10 on the left side. And as you approach from the right, as x approaches 5 from the right, these numbers are starting above 10, but they're moving closer and closer to the number 10. And since these two arrows are kind of touching each other right here at 10, that means that the limit not specifying a direction, just the limit itself, is 10. So graphically, if you have a graph, you can just visually see as long as from the left and the right, you're approaching the same place on the graph, and that means that is the limit. Okay, so that's the second way to evaluate if you have a graph. Now, some limits don't exist. We don't mean to imply that there's a limit at every x, and limits can be different for different x's. So you can have a particular function, like this function is very complicated. For different portions of its domain, it would be defined by a piecewise function. So for some x's, the limit does exist, but for other x's, the limit doesn't exist. So let's look at each of these cases that are mentioned right here, and we'll take a look. So this structure here just says we want to take the limit as x approaches 2 from the left. So positive 2 is right here. As we approach from the left, that means this graph means we're getting closer and closer to this y value, and that y value is a 1. So this left-handed limit is equal to 1. Okay, well, let's do this one. The limit as x approaches 2 from the right means that we have to approach 2 from the right, which means that the y values are going along this like this, and they're actually approaching a 3. Right now, since those two things are not equal, we have to say that this limit does not exist. So whereas we said that if the two y values are equal, we can declare the limit to exist at that value. If the two values don't exist, or one of the values is an infinity, then we have to say that the limit as x approaches 2 does not exist. It does not exist, or is non-existent. Typically, we use the abbreviation DNE for does not exist, right? So there's no single y value that's being approached when you're in the neighborhood of 2. Sometimes it's 1, but other times it's 3. Okay, now this symbol here, this is different. F of 2 means not a limit. This means literally plug 2 itself, not near 2, but 2 itself into the function. So if that's true, then we have to actually plug this x in, which means we can't use this 1 because there's an open circle. We can't use this 3 because there's an open circle. But right at this value, there is a dot down here that says that if you literally plug 2 itself in, you get -1 as the output. So this is the way that we get the value exactly at 2. These structures tell you the y value in the vicinity of, but not at 2. Okay, and then this next part down here says let's evaluate things at -1. So at -1, the limit as x approaches -1 from the right means we're approaching -1 from the right, and the y value seems to be going off to -infinity. So you can write this as -infinity. It's legal to say this is equal to -infinity, even though that's not technically a number because it's not a finite value. Or you can say that this limit does not exist, and AP will accept that. They seem to prefer that you actually write a -infinity because you get more information from that. You can tell that it doesn't exist because specifically it's got a behavior that is approaching a very large negative value. Okay, this limit down here, limit as x approaches -1 from the left, negative here, means you're approaching this way, and that means we're going off to positive infinity. So this would be positive infinity, or does not exist. And you can never say that infinities are equal. Even if they both approach a positive infinity, you still couldn't say those are equal because they're not numbers. So in this case, either of these being infinity means that the limit by definition does not exist. Okay, look at some other examples here. Now, using a graph or using a table are nice if a graph is provided. Table is the least desirable way to analyze. So the way that we use them most is what we call evaluating limits analytically. And this basically says this. Let's say that you were going to evaluate a limit at, let's say I wanted to evaluate on this one, the limit as x approaches 0 of this function. Let's call it f of x. Well, on the graph, if I can see that as I approach 0 from the left, the y is approaching this value right here, and the value as I'm approaching from the right is approaching that value. In other words, maybe I could say this is equivalent to saying limit as x approaches 0 from the left of f of x, and I get some number, whatever this number is. Let's guess that it's 1.7. Okay. And then I check on the right, the limit as x approaches 0 from the right of f of x is also that same number, 1.7, and that means we can declare this limit as 1.7, right? So the idea behind this third method, analytical, is if the function is well behaved enough that I can literally plug 0 into the function. In other words, if I can plug 0 into the function and I get 1.7, then that means that most likely the function is approaching that value both from the left and the right. Right, so even though we're not literally evaluating at the target value, we can try plugging it in to see if we get a number. And if we get a number, then that is going to be the number that's evaluated, because that means that the function is well behaved enough that it's smoothly changing in this vicinity, and you're approaching the same value as you would by plugging the number in. So let me show you a specific example here. Let's say we've got limit as x approaches 3 of this structure. Right? I can try literally just plugging a 3 in there. That's 3 squared minus 25 over 3 minus 5. And because I'm not plugging a 5 in, this is a place where this function is well behaved. I actually get 9 minus 25, which is, let's see, negative 16. And then on the bottom, I get negative 2. So this ends up approaching 8. Right? And if you were to graph this function, it does have a hole at 5, right? But it looks like a line. It looks like the line y equals, let's see, x plus 5. So it looks something like this. There's a hole here there's a hole here at 5, but we can't plug a 5 in here, but we're evaluating it over here at 3. And if I just plug 3 into the function and I get 8 out, well, that is the number that I'm approaching from the left and the right. So I can just declare that this limit is 8, and we don't have to do any further checking. So analytically evaluating a limit means attempting to temporarily plug the target value itself into the function to see if you get an answer. And if you get an answer that's a finite number, then that is the definition of the limit. That is the value that the limit evaluates to, because the function is well behaved in this region. Okay. But let's say that you try to plug a different target value, like say 5 into that function, right? And if I try to do that, what would I get? Well, I would get divide by 0. Okay, I can already see that this is going to give me divide by 0. Okay, so in that case, I'm not going to actually do what I did over here and show that this is equal to this, right? Because this expression, this limit, is in fact equal to a number, and this evaluates to that number, and that evaluates to that number, and that evaluates to that number, and that evaluates to that number. So these things are all in fact equal. Once I detect that I'm about to divide by 0, I don't want to write that this is equal to something, because this is not going to be a number, right? Instead, I'm going to do this. We're going to say, let's take the limit as x approaches 5 of the numerator, x squared minus 25. And that's 5 squared minus 25, which is 0. And the denominator limit as x approaches 5 of x minus 5 is also 5 minus 5 is 0, right? Which means I've got a divide by 0 situation there. So one thing we can try is if you try graphing this function, let me just show you that this graphs the way I asserted it did on the other screen. If I plug this in, it's already in there, and I graph this, so let's say zoom 6, which is origin plus or minus 10, this is simply going to look like a line. And it looks like I can, in fact, plug a 5 into there. Right? But there's actually a little hole in that graph. Right? Let me draw the graph properly. If we were sketching this graph to try to make it a graph so we could use our graphing method, then this would look like this. There's something that looks like this, but when we get to a 5, there's a hole in the graph. It looks like that. All right, so while I can't actually plug a 5 in, the graph of this appears to be a line. So why does it appear to be a line? Because if you take the integrand here, and use a different color, x squared minus 25 over x minus 5, and you factor the numerator, that factors into x minus 5 times x plus 5 divided by x minus 5, which means you can factor that out, and that would be x plus 5 over 1. And that means that the limit as x approaches 5 of this structure is equivalent to taking the limit as x approaches 5 of this, which is algebraically equivalent to taking the limit as x approaches 5 of just x plus 5 over 1. And now I can safely plug this 5 in here. 5 plus 5 is 10, and that is in fact the number that I'm approaching both from the left and the right. Right, so just as we saw on the first screen, we've been working with the same function, right? If we try numbers from approaching 5 from the left, we get 10. If we try numbers approaching 5 from the right, we get 10. If we graph the function, the graph appears to be approaching 10, but we can't literally plug a 5 in here for the x because that would be divided by 0. But the other way to find that 10, besides having to resort to a table, is if you can factor and cancel out the part that's divided by 0, then you can plug the 5 into the resulting equivalent algebraic expression, and that is another way to get the limit. That is called evaluating the limit analytically, using just algebra to analyze the function. Okay, so this is the fastest and most convenient way to find a limit, so we usually try this first. And then if we can't make this work, we can't find a way to simplify so we can plug in, then we go backwards and look at, can we graph the function, or worst case, do we have to just try plugging numbers in to the left and to the right of the number? Okay, here's a couple more examples that you can try. You can pause the video and try these, and then unpause and see if you got these correct. Okay, let's say we're given this function. The limit as x approaches 0. I can see that if I plug a 0 in here, I'm going to get 0 squared plus 4 times 0, which means we're about to divide by 0. And that means that I'm not going to be able to directly plug in. But I do believe I can factor this. So what I would do to show work is say that this is equal to the limit as x approaches 0 of, let's factor in x out of the top, and let's factor in x out of the bottom. And that means we can legally cancel this x with this x because that forms the fraction 1, so it's removed. So that is equal to this limit as x approaches 0 of 2 over x plus 4, since that's algebraic equivalent. And now I can safely plug in the 0 for this x and get that it's 2 over 4, or 1/2. So this does evaluate, and we don't have to resort to cancellations or using the, well, we use calculations, so we don't have to resort to sketching or evaluating with plugging in values near 0. Okay, how do we handle something like this, a piecewise function? Okay, so what a piecewise function means is that this function has different rules for determining y depending on where you are in the x. So if we want to evaluate the limit as x approaches 1, there's no way around it. With multiple rules in here, I'm definitely going to have to separately check the left-handed limit and the right-handed limit. So let's, on the left, have x approach 1 from the left of f of x. Okay, I would usually write that, and then I will replace this f of x with what the rule is in the vicinity just to the left, to the more negative side of the number line from 1. So this 2 is the rule at 1. This is the rule when x is less than 1. So I'm going to replace this with 3x minus 1. And then I'm going to attempt to evaluate that limit by plugging in. So this I can safely plug in a 1 for that x. 3 minus 1 is 2. That means the left-handed limit is equal to 2. Okay, then I'm going to check the right-handed limit. The right-handed limit would be limit as x approaches 1 from the right of f of x. And now, because this is a piecewise function, we may have a different rule here. So for x's above f1, we have to use the rule 3x. So when I plug a 1 in there, I have 3 times 1, which is 3. And because those two limits are not equal, we have to say that this limit does not exist. What that's saying is if I were to graph this function, let me just graph it really quickly so we can see what this looks like. This is actually the work I would show, but what I'm doing in the graph is showing you what's going on. So this function is at x is 1, it specifically gives the value of 2 as the output. Okay, for all the x's greater than 1, it's a slope of 3 lines. So like this, so something that looks like this, a slope of 3 lines. So over 1, up 1, 2, 3, so something like this. And it's a slope of 3 shifted down 1 here with everything below that. So it looks like we've got, let's see, from the right it was 3 actually. Right. So actually, let me back up there. This would actually be at 3. Like that. And this would be something like this. Okay, this is a slope of 3 line. Okay, so here's a graph of what's happened. When we did the limit as x approaches -1 and we got 2, that means as x was approaching 1 from the left, we ended up with 2 on the left side there. When we checked from the right, limit as x approaches 1 from the right, we saw that this was a 3. And since that 2 and that 3 are not equal, that means there is no limit here because we don't have a single y value that's being approached. Because there were two separate rules, they didn't join up at x is 1. Yeah, you don't have to show the sketch. I'm trying to visually give you an indication of what we're doing when we check the left-hand limit and the right-hand limit. But when we have what's called a piecewise defined function, we're always going to have to explicitly check the left and the right. Okay, here's another case. Let's say that we have something that's not as easy to analyze. It's not just like x minus 2 or x minus 1 on the bottom. What if we have something like this? Well, if I try to plug a 1 in here, 1 cubed is 1. 1 minus 1 is divided by 0. So I'm going to have to try to factor this and hopefully factor out an x minus 1 because I have an x minus 1 here to cancel that. Right, so let's see if this would factor. Is this in fact equal to limit as x approaches 1 of x minus 1 times x minus 1 times something? In other words, could I factor this into x minus 1 times that? Well, there's a quick way to factor. If we think x minus 1 is a factor, that goes to 0 at 1, so you can do synthetic division from Myers algebra 2. So you put the 1, that's the 0 here, and then this right here, x cubed, is 1x cubed plus no x squares plus no x's, and then -1. So this is like the x cubed column, the x squared column, the x column, and the numbers column. Okay, so the way synthetic division works is you bring the first number down, you multiply these two numbers together, and you write the result here. 1 times 1 is 1. And then you add down here. So 0 plus 1 is 1. Then you repeat this. 1 times 1 is 1. You write the result here, and you add 0 plus 1 is 1. And you say 1 times 1 is 1. You write the result here and add 0. Okay, now down here, everything is shifted. So this is actually the remainder. This is the numbers, and this is the x column, and this is the x squared column. So this is 1x squared plus 1x plus 1 with a remainder of 0. And since that remainder was 0, that means this did divide out and leaves the polynomial x squared plus 1x plus 1 left. So you can use synthetic division to try to factor out this, because now these cancel, and this is equivalent to the limit as x approaches 1 of 1 over x squared plus x plus 1, which means I can plug in a 1 for these x's. 1 squared plus 1 plus 1 is 1 over 3. And so that evaluates to the value 1/3. Okay, I think that might be the last example. Let me see real quickly here. Okay, let me summarize real quickly. We defined a limit to be if there is a single y value that's being approached, no matter what direction you're approaching in the domain x, then that number is declared to be the limit. The way we write that is the limit as x approaches the target value in the domain of some expression for the generating the y, the function, is equal to the numerical value of the limit. As long as that is a finite number, then that means that we can declare the limit exists. You can find that, compute that value by plugging numbers in a little below and a little above the target value to see if they are approaching y values that are the same. That's called evaluating the limit numerically. If you happen to have a graph, you can see visually whether or not the y's are approaching the value, same value as we approach from the left to the right. And if not, you can attempt to evaluate analytically. So you can try plugging in a number. If you happen to get a numerical output, then that means the function is well behaved in that region, so you can use that number as the limit. If not, you can attempt to do things like factoring and canceling to allow you to plug in a number, because if you write an algebraically equivalent expression for this, the graph is the same, which means the y values will be the same. And then finally, the limits don't have to exist, and their existence is unique for every x. So you can have a function that has limits that don't exist, say at -1 and at 2 and at 3, but they exist at all the other x's. All right, I think that's it for this video.